So this is our boat project by the Barnacle Boys, and our team members are Gabe Galvez, Wnek, which is myself, and Nick Trejo. So our project's topic was exploring how we can use the principles of applied engineering and chemistry that we're learning in order to help solve problems, for example, the lifespan of marine structures exposed to salt water. So our project goes in and overviews in depth the various ways that seawater corrosion and wave erosion have on the degradation of common marine structures and building materials such as steel and concrete, and also the shapes that can possibly help divert and resist these the erosion of the seawater and the waves. So group member responsibilities. So Gabe Galvez was responsible for collecting pictures and data. I was responsible for organizing and managing group meetings, and Nick was responsible for finding sources and proof checking everything. Our proposal that we actually ended up going with for this project was, as you can see here, how the various aspects of water cause the corrosion breakdown of common marine building materials such as concrete or metal, in this case steel. Furthermore, what's being currently done to prevent this breakdown of material and how we can further implement this. So the main challenge our group members had to work around would be our class schedules, but we solved that by meeting at night in the library. So as you can see, the main components of seawater is sea salt. So that tiny little 3.5% that you can see is mostly made up of chloride ions and sodium and a little bit of sulfate for the most part. And this is harmful to concrete because concrete is rebar. It has a low tensile strength. That's why it needs rebar to help support it and give it added strength. However, these chloride ions can seep into the structure of the concrete, and consequently, they can actually cause a phenomenon known as a corrosion cell to occur, where essentially the electrons in the whole mixture, because again, these salts act as an electrolyte, start moving around, and you can see that that can actually cause corrosion and rust. And of course, rust is bad because it expands, and you can see that's exactly what happened with the SS Selma shipwreck, or this damaged segment of the Pelican Island the Pelican Island Causeway Bridge. You can see that rust takes up more volume and then the raw rebar would, and this actually goes along with how I was saying earlier that the rust, it will basically break and crack the concrete, exposing it to even more seawater and perpetuating this cycle of corrosion and breakage.
Well, I wrote about in the presentation on how we could reduce the effects of erosion using the shape of it, because the shape of the foundations plays a critical role in diverting the water away from the foundations and the base, because it causes a smoother flow around it and just increases the lifespan of the foundation altogether. Oh, and in these photos right here, we could see that in this bridge, not only are the bottom parts of it very skinny so that the water can easily flow around it, but also it's not shown in here, but this is going with the flow of the stream, so it doesn't interact with it too much, thereby reducing the amount of erosion that the foundations would face. And then next I talked about the reasons why the shape would matter so much. So in these diagrams, it shows how fluids and air would flow around objects and how their shape could smoothen their flow. Because right here with a flat surface, there's lots of drag, and that would, with water and concrete and other materials, that would increase the erosion that it feels. But with smoother surfaces, it flows around it, and it's not as dramatic of a problem whenever it's smoothened out. And it's important that there's not that much forces acting against the foundation, because each wave has approximately from 250 to 6,000 pounds per square foot in each wave. So in offshore oil rigs that are pounded by waves daily and very frequently in that day, it's very important that they don't feel the full force of that wave every time it crashes, thereby making it last longer. Because if it felt the full force of it every time, the foundations would crumble in no time.
That we took of the Galveston Causeway Road Bridge helped us demonstrate that in certain marine structures that we can design in the future as future engineers, they take special care to prevent damage from the kinetic energy of these waves that Nick was talking about, as well as protect the metal from corrosion and chemical leaching. And here is the bridge, and here's where it's at. So how does this affect the environment? The possibility of large-scale metallic corrosion can lead to many negative effects, such as the production of plant shutdowns, which means basically the plant just dies because of the contamination that happens in the water, which I talk about in that point, and the waste of valuable resources. What scientific areas study and work to solve our problem? So corrosion science is an interdisciplinary field involving the study of organic chemistry, microbiology, electrochemistry, metallurgy, and more. Hydrodynamics, which is kind of what Nick was talking about, how the waves form around so it doesn't feel the full force, mainly involves mechanical engineering, but it also involves physics, of course, because dynamics and kinetic energy. So the photos that we included that you've been seeing throughout the presentation support our topic because we are trying to research ways to support the lifespan of marine structures. Many of these have shown mixtures of actively used engineering/chemistry applications to prevent various causes behind seawater corrosion. However, some of these structures we took photographs of could have certain things implemented. For example, materials resistant to the corrosion damage caused by the infiltration of seawater and its ions, marine construction and material shape and design to prevent corrosion, some form of shielding and protection from corrosion such as a galvanized layer of paint, various barriers protecting and mentioned marine structures from the seawater moisture such as paints and sealing coating that I was just talking about. So, how would our future engineering careers help us analyze and improve the way we deal with these sorts of challenges? In chemical engineering/material engineering, we could find metals or alloys that are resistant to corrosion and find the chemical paint that we could use to cover metals to shield them from corrosion. And with mechanical engineering and marine engineering, of course, we could find shapes that can prevent the amount of erosion over time for boats and other marine structures. Thank you.
So last but not least, these are our references. This is our bibliography. We have all of our sources that we used here in APA style format. Thank you for watching our presentation.